All right, the second part of 16.1 is looking at rate mechanisms. So it's a different way to determine what the rate expression or the rate law would be. Most reactions involve a series of small steps. How do we know this? When we go through, and if you remember the titration method where we would quench a reaction and then titrate it and so on and so forth, well, that happens when we periodically stop a reaction and go through and identify what products are present. There are products there that we didn't expect to be there. Therefore, it is believed that reactions occur in series of steps instead of just going straight from reactants to products, but intermediates are made. So each involves a small number of particles in each step. And this whole thing is called the reaction mechanism. The reaction mechanism is a theory about the sequence of events from reactants to products. And the thing is, it's a theory. So we do not know that for sure, and it's based off consistent observations with data. So what does this look like? So I'm going to show you a reaction and then walk you through what it is. So we have step 1 reaction. So here we have NO2 reacting with another NO2 to make NO and NO3. Step 2, NO3 is present with CO, and that reacts to form NO2 and CO2. But the overall reaction we're looking for is NO2, CO, and NO and CO2. All right, well, how do they get this overall reaction? This is very similar to Hess's law. So if you remember going through and canceling out commonalities and stuff, so that overall reaction is the sum of the individual steps, and they must be equal in order to become an overall. And where this happens is the intermediates on the first product of the reaction and the second reactants should cancel out. So let's identify our intermediates. So looking at the reactants of step 2 with the products of step 1, NO3 is present in both. Therefore, NO3 is what we call an intermediate. It was made to help make the ultimate final products as well. So we identified our intermediate, and our intermediate should therefore cancel out, which it does. Now we need to go through and make sure everything else cancels out and or equals our overall reaction. So we know we have to have one NO2 in the overall reaction. If we look at the second NO2, that actually cancels out with a product in step 2. That CO matches, the NO matches, and the CO2 matches. So we've crossed out everything that is common, and then we've made sure that what's left behind is what we see in that overall reaction. So these guys, step 1 and 2, these are called your elementary steps. And these usually cannot be observed individually. They're just happening as it goes on. And just like we said, they may have stopped the reaction at one point, and they're like, whoa, where did this NO3 come from? This was not expected, this was not predicted, and therefore they go back and they tweak what this mechanisms can look like based off different times they stop a reaction. So there's this concept of molecularity, and this indicates the number of reactants involved in the elementary steps, not, and I repeat, not in the overall order. You can have unimolecular, so there's only one reactant in the elementary step, so it's going to be a decomposition reaction. And it can be bimolecular, which means you have 2 reactants present, which is the most common. There is theoretically a trimolecular. However, the possibility and the probability of 3 reactants finding each other at the right time with the right energy and the right orientation is highly unlikely and therefore extremely rare. So how do we use this rate mechanism in order to determine what the rate expression should be? Well, we have something called the rate determining step, which I will shorthand from now on as RDS. And this is the slowest step in the mechanism, hence it's rate determining. You can only go as fast as the slowest step. You can only hike up a mountain as fast as the slowest person in your group if you're being a good person, right? And you're only as strong as like the weakest chain, all those silly little sayings, but it is consistent with what has to happen here. So the product of the reaction will only appear as fast as the products in the slowest step. Therefore, if we look at this graph, so we have potential energy, right? We can see this. We see that it's an enthalpy diagram, and we have our reactants, we have our products, we have our delta H, we have our EA, so our activation energy. This looks a little different because they've actually taken just the one reaction that we'd expect from reactants to products and broke it out into their elementary steps. All right? And so if you look at the hump of the first, it takes more energy to get over that first hump than it takes to get over the second hump. Therefore, that first step is your rate determining step, right? Because it has the highest activation energy. So if we were going to use a catalyst, where would we want to target that catalyst? It's going to want to be targeted at the highest activation energy. Therefore, we want to pick a catalyst that is going to affect particularly the reactants in the first step, or the rate determining step. And this could be vice versa. You could have had a graph where the second hump would be your rate determining step as well. And I know that's a beautiful drawing, right? So as we said, rate law comes directly from the molecularity of the rate determining step. This was mentioned back in the first video when we're looking at the rate expressions and how do those orders actually come about besides experimentally. So if you have one reactant and it's going to go through and make your products, that's a unimolecular reaction. Therefore, rate equals K times the concentration of A. And if you look at this, this becomes a first order reaction. If you have a 2A reaction and that to make products, you have a bimolecular, and your rate becomes K times A squared. That's a second order reaction. You have A plus B to make your products. That's a bimolecular reaction because there's two parts. And the rate equals K times A times B. Again, the way it's being represented right now is a second order reaction. But those values here could theoretically change individually. So the rate, how do you get the rate law from, or you get the rate law from the rate determining step, and that's going to give you your rate expression. So what does it look like and how do we determine this? It has to come from the slowest step. Therefore, you have to determine which one is the rate determining step. So first thing you do is you stop, look at what's provided to you. And so in this problem, slow. That's what I'm looking for. Which one is slow? Step 1. So that's where I'm going to focus my energy. Okay? So I'm going to go through and I'm looking at all my steps and I'm looking at my overall. I want to make sure everything matches up. I'm going to go through and identify that it all works, right? So do I have an intermediate? Yes, I do. It's chlorine gas. So I'm going to take care of that, right? And then I'm going to go through and say like, okay, so I have 1, 2 NO2s, perfect. I have 1, 2 NO2s, perfect. And I have 1 Cl2, perfect. Okay, we are good to go. So now what you have to keep in mind is that everything's based off the slowest step. So that means NO2Cl. It is going to control the rate in which NO2 and Cl gas are produced. And that Cl gas is used as a reactant in the second step. So the speed in which that Cl appears is the speed in which it can get used to make the final products in the reaction. Therefore, the whole rate of this reaction resides on the ability to decompose NO2Cl. Therefore, the rate expression is rate equals K times the concentration of NO2Cl. Please notice that it's a first order reaction because there is only one NO2Cl in the first slow step, and it does not matter that there was one in the second step because that doesn't control the rate of the reaction. This is a unimolecular reaction then, and it's a first order. Well, let's make it a little bit harder. So once again, identify your slow step. This time, it's in the second step. All right, so what we need to do is go through and we need to look at identifying, again, intermediates, so on and so forth, right? Okay, so going through, and I see that N2O2, and N2O2 cancel out, all right? So we have two NOs, O2, O2, two NO2s, two NO2s. Sweet. So everything's accounted for. Okay. So you're like, this is easy, right? So if I'm in my slow step, I look at the reactants of that slow step, right? So I'm going to look at that, and you're going to think, well, this is easy. Rate equals the concentration of N2O2 times the concentration of O2, right? You're like, score, done. Not. Problem is, N2O2 is an intermediate, so therefore it cannot be part of the rate expression. And because it's an intermediate, the concentration of N2O2 available to run that second step solely resides on the ability of the NOs in the previous to make that N2O2, right? So the products of the first reaction's concentration depends on its reactants. Therefore, the rate truly is K is NO squared times O2. Because N2O2, the production of N2O2 is controlled by the reaction with NO. Looking at this, this is a third order reaction, right? It is, and this is where it gets a little tricky. You're like, well, there's three of them. There's three present. So this would be trimolecular. But because it's happening in two different steps, it gets a little tricky there. Okay? Okay. So remember, the order of the reaction is connected to the rate determining steps coefficients and not necessarily the overall order of the reaction. And so if you looked at the last example, it happened that the rate expression matched that of the stoichiometric equation, but the first one did not. So you need to be careful and make sure you're watching out for that. So how can zero order reactants appear then? We discussed this in the first video. See, if you have a reactant, it should take place in the reaction and it should affect the reaction. Well, zero order reactants exist because the reactant does not take part in the rate determining step. And therefore, it's there to help react, but it's not there to determine rate. Possible mechanisms are due to theory. They're empirical findings, and so they're always being modified. And so when they do not satisfy, they're going to be rejected, and they're going to go back to the kinetic data and the stoichiometry and figure out what could a new mechanism look like, then redo the experiment and keep modifying it. So it is a theory. It's never at this point going to become a true law, but they can, as technology gets better and better, they can go through and modify as necessary.